Hello, I'm Andres Rojas from StarLab, and I'm presenting the poster prediction of minimally conscious state responder patients to non-invasive brain stimulation using machine learning algorithms. This work was carried out within the Luminous project and together with the Coma Science group from Liège. In the context of this study, we worked with coma patients in minimally conscious state who received transcranial direct current stimulation to promote coma recovery. Transcranial direct current stimulation is a technique that modulates the electrical activity of specific regions in the cerebral cortex, and it is believed to promote coma recovery in this kind of patients. We hypothesized that by using EEG data previously acquired to 3DCS and machine learning algorithms, we could predict patients that could respond well to this kind of therapy in the future. The goal of this study is to match patients to the right treatment, to speed up patient recovery, to test the viability of EEG data as a predictor of neuroplastic response, and to build an EEG-based decision support system for early detection of responder patients. This experiment is a randomized double-blind sham-controlled crossover study. 17 patients were in unresponsive wakefulness syndrome. 21 were in minimally conscious state. From these 21 patients, 6 patients were responders to TDCS, and 4 patients were discarded because of bad EEG quality. For the methodology, we followed a machine learning pipeline in which data was acquired using EEG. We preprocessed the EEG signals, applying the trend, the mean references, cutting the EEG in epochs of 5 seconds, and bandpass filtered in the frequency bus of interest. As feature extraction, we extract the relative band powers in theta, theta, alpha, beta, and gamma, and we use TSNN for dimensionality reduction and visualization of the features, and also as a feature input for the classifier. For the classifier training, we train in support vector machines and random forests, and we use the owl rock and leave one subject out for the performance metrics. In order to cope with the challenge of such a small data set and a very noisy data set, we used Bootstrap for augmenting the data set, and we kept the intersubject variability of the EEG. Although we didn't carry out a statistical significant study of the features within the responders and the non-responders group, we analyzed the feature distribution of the most relevant features using the feature important values of the random forest, and in order to look for potential EEG markers, and we visualized the RBP features in a reduced dimensionality space. As a result, we found an accuracy of the owl rock of 80% with the random forest algorithm at epoch level. It means that from all the epochs of all the subjects, we correctly classify 76% of the subjects. That's the accuracy at subject level. For support vector machine, we obtain an owl rock of 82% for all the epochs, 94% of accuracy for subject, which means that from the 70 subjects, one of them was not correctly classified. As important as the classification results is the future importance and in the interpretability. We believe that there are potential EEG markers that could be finite and with statistical significant studies and with a bigger data set, And these markers could be used for consciousness recovery, and this would be aligned with a trend in building translational neuroimaging markers with this with other technologies such as neuroimaging. We have proven the viability of using a spontaneous EEG to predict patient response. We have identified potential markers as low beta in frontoparietal area and alpha in the parieto-occipital area. We believe that the use of such models will be improved with a larger sample size, and this can be extended to other disease and not only MCS. And this can prove that EEG is a potential candidate for building machine learning algorithms in decision support systems for health applications. Thanks a lot for your attention.